Hi everyone, welcome to today's session. Starting today, we will dedicate each session to exploring different principles of system modeling. Let's kick things off with a quick poll. Robs, if you can start the poll. So let's get started with a basic question. Like, first of all, do you feel there is a need for principles while modeling a system? Uh, right. And then we will explore if there is a need, how does it help? Yes, so most of us feel that there is a need, and some are not sure. Hopefully, by the end of this study group, they will be sure. Let's see. Okay, Robs, I think we can start. Why do we need principles for modeling systems? Imagine you're looking to buy an air conditioner for your home. Naturally, after being comfortable with System Modeler, you decide to model your room to test out various air conditioners available in the market. Initially, your enthusiasm is sky high, but as you face the blank canvas of the modeling interface, that excitement might quickly turn into overwhelm. Questions start flooding in, like how should I start? Which software or library should I use? What parameters should I include? Do I need to account for heat loss due to air leakage through windows? And that's just scratching the surface. As you delve deeper into creating your model, it's easy to lose track of the assumptions you made early on, leading to potentially incorrect conclusions. This scenario is all too familiar not just to beginners but also to experienced professionals like myself and many of my colleagues. Despite years of modeling experience, we still encounter these challenges, though perhaps to a lesser extent now. In the upcoming sessions, we will delve into these principles one by one. These principles are inspired by the insightful book Model Bygge och Simulering by Lennart Leung and Torkel Glodd. This book is in Swedish and the title translates to Model Building and Simulation in English. While we will draw from this book, we will also share principles that we have learned from our modeling experiences. These principles are practical guidelines that help you get started and importantly keep you grounded. They encourage you to critically assess your model at every stage, ensuring that your conclusions are as accurate as possible. Having considered why principles are important, let's now begin with the principles that you most probably would have heard in one context or the other. That is, start simple. The importance of this principle is easily summarized by this quote that is attributed to Francis of Assisi. Start by doing what's necessary, then do what's possible, and suddenly you're doing the impossible. Let's look how this principle is applicable in different fields, and then we will see how it helps in the modeling process. Imagine it's a new year and you're determined to boost your savings. You might start with an elaborate plan covering everything from budget tracking to investment strategies. Yet, as the daily life proceeds, the complexity can become overwhelming, leading you back to square one. However, by starting simple, perhaps by just logging your daily expenses, you set a foundation that's easier to build upon. The concept of start simple is used in many domains. For example, in software engineering, starting with simple and modular code is important for maintainability and scalability. Programmers often begin by writing small, well-defined functions or modules that perform specific tasks before integrating them into larger systems. By starting simple, programmers can easily debug and modify code, accommodate changing requirements, and scale the system as needed. Similarly, when designing electrical circuits for electronic devices or power systems, starting with simple circuit topologies is important for reliability and efficiency. Engineers typically begin by considering basic circuit configurations before adding more complex components or features. By starting simple, engineers can minimize the risk of electrical faults, improve energy efficiency, and reduce manufacturing costs. Finally, in the design of control system for robots, vehicles, or industrial processes, starting with simple control algorithms is important for stability and performance. Engineers often begin by considering basic control strategies such as a PID control before adding more advanced features or optimizations. By starting simple, engineers can ensure that the control system responds predictably to changes in the environment and achieves desired performance objectives. Similarly, when you create models, starting simple has several advantages. Sometimes, by starting simple, you realize that there is no need for a complex model to reach your objective. Let's say you are modeling for the techno-economic feasibility of a solar PV plant. You are interested in the long-term performance of the photovoltaic plant as you are looking at a simulation period of several years. If you start with a simple model, taking the best case scenarios, and you discover that the project is economically not feasible, then probably there is no need to add more details like how the shadowing on the PVs would have an impact on the power production, or how would the temperature management system of the battery pack cope with the harsh climate, and so on. Sometimes the objective of a model is to come up with the simplest model possible. For example, let's say you want to use a feed-forward controller that you want to deploy on real-world hardware. These controllers use a model of the system to operate. If you use a very detailed model for such controllers, then your controller might be computationally expensive and needs more time to respond to change. This, in certain cases, will make the controller unusable as these controllers are expected to respond at very high speeds. Finally, starting simple helps you in understanding your system. A simpler model with a smaller number of parameters would allow you to use model calibration, test uncertainties in parameters, and check sensitivities. As you create a more detailed model, doing such analysis becomes very computationally expensive and might fail in unexpected ways. Having considered how starting simple helps in modeling, now let's think about modeling the spread of an infectious disease. By applying the start simple principle, we will focus on modeling the key dynamics first, adding complexity only when necessary. This approach not only makes our model more manageable, but also ensures we can adapt and refine it as we learn more. During the pandemic, you might have seen a curve like this and heard the term flatten the curve. Let's try to model this phenomena using a simple model. It is simple yet powerful enough to understand an important concept. Here is the model that we will try to accomplish by the end of this session. Let's start the modeling process step by step.
Right. Um, so we have so Vedat is sick today, unfortunately. So I have my colleague Leonardo with me today, who will help, and Sergio as well. And Leonardo and Sergio will help me in today's hands-on session. Leo, if you can switch on your camera. Right. Okay.
Hello.
Yes. Yeah. So Leo, so the objective for today is to we are covering the concept start simple, and then I thought this example of modeling this spread of an infectious disease would be really nice to get started. So how would one start, Leo? Like, let's say we want to model, we have a modeling objective, for instance. to model the spread of an infectious disease, how would one start modeling a process? Like, should one start by thinking about the equations, or it would be nice to start looking for libraries first, which have components that is needed for your modeling process? Like, how would you start, Leo, if you have a modeling objective? Like, how do you usually start in your projects?
I guess that it depends really on the experience of every person. Like in my case, I'm an electrical engineer, and in the modeling lessons, we learn a lot about how there are analogies between the different domains. So I will start trying to model things as electrical circuits, but since probably it's more difficult to find how to model a pandemic with
Yes.
resistors and capacitors, the the best thing will be to search how pandemics are modeled, right?
Yes, and the model that we are going to cover today is called SIR model. I think most people would have already heard it at one stage or the other. And this model has been in existence, I think, since 1940s. And so, what this SIR model? So, for people who are hearing the term for the first time, which I doubt, but still, what this model says is the entire population group is divided into three different categories. One is susceptible, one is infected, and recovered. So the entire population group is divided into three different categories, and once there is an infected person, then it gives the equations of how uh, like the infection spreads across a susceptible group, right? So Leo, there are two ways of starting to model such scenarios. Like, first, look for equations, create your own differential equations, or as you said, look for analogies, or look for libraries that you are comfortable with. And for today's session, I have provided the components package inside the Start Simple sub library, which we are trying to use and try to understand the SIR model. Right. To get started in the step one, uh, like when you start testing a new library, the best way is to start with just testing how the base components work, right? And in my library of Start Simple, I have you could see four different components. So let's start with the step one of just dragging in the population group. I have done it already, but let me try to do it again for the fun of it. So the first thing is, let's start by dragging the first component to our modeling canvas, and you can use the exercises folder and start with step one. Okay, let me do that myself as well. So people who are following this with System Modeler, you can open the step one file under exercises and drag in the population group, right? So once I have my first component, I could see that I have a parameter here which through which I can define the initial population. And here it's defined as 100 people, right? So once I have this model, I want to know, is there any dynamics hidden inside it, or how does this work? So in order to understand how this particular component would work, I would just start by simulating this simple model with just the population group. In some case, in some libraries, you have a component which have some internal dynamics as well, and you want to explore it so that you can understand it better, right? So once I simulated my model, I go to Simulation Center, and then here I can see the different parameters that are present inside my component. For instance, I can plot the display population, or I can plot the initial population, and I could see that there is nothing interesting happening. So in this population group, I started with 100, and at the end of the simulation, I have 100 uh, people. So there is nothing interesting happening, right? Um, okay. So this step. So once I know I just have population group, the next thing I would want to do is, let's say in the SI concept, let's start by modeling the S and I. Like, let's start with two different population groups, one to represent the susceptible group and one to represent the infected group. We will cover the recovered group as we go along. So to model that, I will drag in two population groups, and then I will start by renaming this groups. So in order to rename, I can right click and go to rename option over here, or you can click a component and press F2, and then you can give it a suitable name. Let's give it susceptible. Let's give it a name, susceptible. And then I will change the name of the other group to infected. Right. So now I have two population group. If I don't do anything, then you know that the population will remain constant, as we saw in the first model, right? To make things interesting, let's add let's start by adding a simple transition element to it, right? And then I can rename it to just transition for now, right? And if I click on this component, I can see that I can specify a parameter for this component, and this is transmission rate. So I can see that it has a unit defined in per day. So let's say I define it, let's say, for 2 per day, and I will give initial values to my susceptible and infected group. So for susceptible, I start with 100, and for infected, I have it 100 as the default. Let me change it to 1 for now,
So
right?
the transition means that the 2 per day means that two persons are going to transition per day,
Yes,
right?
that is like, without knowing anything and just reading the parameter name, that's what I could think of. But through this process, I'm trying to use this component in a model and trying to verify if my understanding is right or not. Typically, when I use a library, I would start looking at some simple examples as well, and then try to understand each component. And then I would start by using the base components and try to create simple models and try to see that the assumptions that we make, uh, if if it corresponds with the model, right? So once an- so far, I have two population groups. I renamed it to susceptible and the other one to infected, gave it initial value. Then I added a transition component and gave it a value of 2 per day. Now let me connect it. As I said in the first class, you can connect it either by clicking on the connection line tool or by pressing C on the keyboard, right? So I will start by pressing C on the keyboard, and then I can connect my components, right? And once my components are connected, I can go to the experiment setup and then set the number of days. In this case, I already set it to 10, but yeah, I can change it if I want. But for this case, let me start with stop time of 10, right? Okay, once we're done with this stage, then I can simulate and check the results. I've, I will give a few minutes for people to try it on their own. And in the meantime, Leo, we can explore how the results look like, right? So once I have simulated, let me go ahead and plot uh, the population in my susceptible thing. Right. So I have a change like this, and then I can then plot the infected group, and you can see that I have this uh, discrete behavior where the the number of people in the susceptible group is decreasing and the number of people in the infected group is increasing. But perhaps this plot is too big, and then I think it would be better if I try to plot this in a different subplot. So to plot it in a different subplot, I can click on my plot variable, like I can click on the plot and then do move to and then I can do new subplot like this. So here, at least my y-axis is more, I can easily understand this better. And here you can see how the transition is happening. So I had 2 per day. So it's from 99. I could go to uh, here. I could go to the day 2, and I can see that for now I have around 5 people, uh, uh, around 5 people who have moved from the susceptible to the the infected group. Right. Right. So Leo, do you have anything to add here?
So what happens if we simulate longer? So it will every all the persons will move to the infected, right?
Yes, and that will also and that way I can also discover a bug, I guess. But let's simulate it for a longer time. So let's say we want to simulate it for stop time goes to 100, and then uh, I can simulate it. Uh, and from the and you might think it is correct, right? But as soon as uh, I try to visualize it better, let me use a plot theme so that I can see the results properly. So you can see that I actually land up in a bad state. So my model has a limitation. Like I in my simple library that I developed, I didn't care for a event which detects that my population has gone below the limit, right?
Yes.
So so this actually tells me that I can only simulate it until I reach the zero value, and probably my library is not good enough to model those intricate things.
But I know what's happening. There are people that is being born infected, so they become immediately
No, I
part
don't
of the
have.
infected. No,
No, I don't have it in the model. But yeah. Okay. Anyways, let's try to simulate it for something much more. uh, so I don't spend time on showing the buggy thing. Let me simulate it for a smaller time of 30 days instead. Right. Okay. So here we saw this nice looking behavior where we have two different groups of people, susceptible and infected, and we have a linear transition from one category to the other, right? But you and me know that this is not how it might work, because if you try to understand this transition, you might think that as we have a lot of people in the susceptible, so you might that initially the transition should be faster, and as you have less people in the susceptible group, and the rate of transition would decrease, right? You would kind of think that the transition should be proportional to the number of people in, let's say, in the susceptible group, right? So so now we have seen the library has two components. In the first like the population group and the simple transition through which I can model a linear decrease. In some cases, of course, if you are modeling something else, maybe this is what you exactly want, where you have a rate which depends on per day and there is a limit to it. But in our case, where you're trying to model a susceptible and infected, probably that's not what we want to model, right? So now let's move back to our model and then try to update it further, right? Okay. So the next component, I could see that in my package, I have a quantity dependent transition. So let me uh, delete my transition element for now, and let me bring this in. Right. Okay. So now I have this new component in my library which has this symbol which tells me that it depends on the quantity that I can infer from the name of the component. And I could see that in the symbol it has an arrow symbol which kind of shows a dependency to the initial group. Okay, so now once I have the component, I will click on it, and it also has the same factor. And let me just give it 2 per day, the same factor. And now let's go ahead and connect it. And this time I will use the connection line tool. I will click on the connection line tool and then connect my components. And the other, and keeping the other um, values the same, right? And then let's move ahead. Since in this model I had already set the experiment date, the stop time of the experiment, I don't need to redo it again. Let's go ahead and plot this. Right. And here we have something really interesting. So here, if I try to zoom in, so let me just remove my measurement points. Let's say I want to zoom in between 0 and 5 days. Uh, it's very fast, but let's zoom in into this particular time range. In order to zoom in a plot, you hover near the timeline, near the time axis, and then try to click left, click the left button of your mouse, and then try to select the region that you want to zoom in. So here I started zooming in from 5 to 0, and then you could see that I have a weird looking plot like this. And that is because maybe my variable step solver was not good enough in, or it missed some of the transition points. Maybe I can transition points. And one way to solve it probably would be try different solver. For instance, let's say I try explicit Euler uh, solver and try to give it 0.001 and try to simulate again, right? And you could see that by using a explicit Euler, I didn't use a variable step solver, but I forced my solver to take some particular step, and then now I get a smoother curve instead. So
So
Leo, do
what
you want to
happened?
explain what happened here? Why?
Yes, what happened there? It is that the solver, that the advanced solver is trying to go as like faster,
Mhm.
and it determines that I can make like a large jump and still get correct results. So it made a large jump, and all that information was kind of lost.
Yes,
So basically, it's a matter of limiting what's the largest step, and in this case, the explicit Euler solver, you are specifying what's the maximum step that can be made.
yes. So perhaps when we are trying out a new library with new components, it's also good that we can find out this type of behavior. So if something like this happens, it may not be because of it's a different process, but it might be just as a result of using not using the right solver steps, right? And it's best to try out with different solving strategies.
Yes, in this case specifically, it was a little bit the solver made its steps because you have like a discrete system. You are jumping from day to day.
Right.
But if you have like a continuous system, these problems will not occur.
Yes. I think this is because I tried to uh, in this component I used inefficient strategy. I used a continuous model, and then I used a real to integer conversion to get this values in a discrete manner. Perhaps there are better strategies of doing that. Right. Okay. Anyways, but now we could see, and okay, now if I want to get back to my initial zoom level, I can double click on my plot, and that will help me in getting back to the original state. So now I'm in its original state, right? So now we have a behavior which we might which might be the right behavior. Like you can see that At the start we had a high transition rate, and as the population in the susceptible group decreases, the the rate um, the rate goes down, the transition rate goes down. And perhaps now we should try out different parameters for the transition factor and see how it would um, affect my model. And people who are trying out the model, they can also try out the different solver steps, try to play around with different stop time, and try to see how your model is behaving. Right. In the meanwhile, I will go ahead and try to add a slider so that I can quickly iterate through various transition rates and see how my model behaves. Right. So in order to add a slider, I will click on the new control panel. I will give it a name. For example, let's say model parameters, and click OK. So now I have a blank control panel with the name of model parameters. And now let me go ahead and add a control object. To add a control object, I will press the plus button and then click on the control object here. And then I want to modify the transition rate. So I will click the transition, the down arrow near the transition, and click factor, right? And then I can either use the description that is provided in the model, or I can write my own description. For now, let me just use the description that was provided in the model, which is just transition factor. And let me add a control type of a slider. Let me change it, let's say from 0.001 per day to 5 per day. I knowingly avoided zero because sometimes it leads to singularities or some weird errors. So I try to avoid using zeros when I try to test different scenarios. And then let me click OK. Okay. Now if I slow down, then you could see that the rate is decreasing. Yeah, as I go towards zero, as the rate goes down, of course, the rate decreases and I have a much slower process. But as soon as my transition factor, I increase it, I have a very fast process.
Ankit,
Hmm.
if I understood correctly, this kind of transition
Hmm.
means that if you have like a larger population,
Hmm.
they will there will be like more people transitioning into the infected,
Hmm.
and as the population is reduced,
Yes.
there is less people transitioning, so it will be like uh, having less of the non-infected people in touch with each other, like in contact.
Yes. Uh, yes. So, okay. Uh, so what happens here, as you can see, is initially for this particular model, at the start we have a high uh, rate, and at the end the rate, you can see the number of infected people goes to saturation since everyone has been infected, but that's how it goes. But in this case, yeah, that is something is weird, right? Like, is as the number of infected people grow, initially there is no infected people, but still we could see that uh, there is a high rate of transition even if there is only one, let's say only one guy who is infected, but the initial rate is very high, right? And that doesn't seem uh, that doesn't seem right. Is that what you want to say, Leo?
Yeah, I was thinking a little bit from the opposite perspective, but yeah, it makes it, you're right. It doesn't make much sense that one person can infect like so many
Yeah,
unless.
yeah. So this doesn't look uh, this doesn't look right. So what is happening here is we are not taking into account how many people are actually infected, and we are just concerned with how many susceptible people are there. Perhaps that's not the right transition that we should use, right? So let's go back to our library and see if we have any other component that we can try and see if that model makes sense. So let's get back to model center. um, I hope Um, yes, I think let's keep it here and wait for 1 or 2 minutes for people to actually try it out. So in the meanwhile, let's ask Sergio if there are any questions that we should try to address.
Uh,
Meanwhile,
right, we have some people asking about. Well, okay, so we have someone asking that if they said instead of using differential equations, they wanted to use like an agent-based modeling or some kind of other modeling for the seer. Um,
right. Uh, we currently, of course, one could do different type of models using the Wolfram language, but with System Modeler, I am not aware of a library that allows that makes agent-based modeling much simpler. I am aware of 1 or 2 library developers exploring that option, but for now we use the um, and this approach is called the system dynamics approach, which we will cover in more detail in the upcoming sessions. But for now, I think we are more into system dynamics or discrete event modeling, you could say in some sense. So either discrete event modeling or system dynamics approach. Agent-based modeling, uh, we, have, we cannot do, or I'm not aware of a library that does that using Modelica.
all right, and then other people are asking about the versions of in English of the book that you mentioned.
Yeah. So this is the book. Uh, I found it really difficult since we are based in Sweden, and this book was and the place uh, where we are present is called Linköping, and this book was by one of the professors from the Linköping University. So that's how I got used to I got in touch with this book. I did try, but I could not find it in English, unfortunately. But I will look look for more. I will have a look, and if there is English version, I will put it in the community.
All right. Yep.
Right. Okay. Right. Okay. There is one thing that I didn't do. I didn't save my plot, and that's something I should not do. I should save my plot. So, to save my plot, I will click on the not stored uh, option on the top right here, and then I should click add plot to model, and then I will give my title as my analysis and set it to default and click OK. Right. So now I have saved my plot in the model plot, and then I can refer to it the next time I simulate. Also, one question that we got during we got in the community was why this thing this the name of the plot, which is my analysis, turns black. Unfortunately, I cannot zoom in further for people who are looking at it at a smaller screen, but here the text my analysis goes black. And when it goes black, it means that there is no changes that is made on the plot, and you don't need to update anything. As soon as I would add another, or I would uh, uh, do some change to the plot, like let's say, let me add an initial population to it, then you could see that now the black thing has turned blue. And if I click it, it comes with different options, like either I can reset to stored, so my current changes will be deleted, or I can update plot in model, so my current changes, like uh, the new variable that I added, will be added to my model plot, or I can create a new model plot, or I can create a new plot from it altogether as with a different name. So those are the three options that I have. So now I will just click reset to stored, and then you could see that it removed the changes that I did. So let's say you have a model plot, you did some changes to it, but you don't want to save it, then you can click on reset to stored, and then you will lose the changes. Or if you want to store it in a new plot, you can create a new model plot from it as well. Okay, so let's get back and try the other component that is present in our library, right? So I will remove transition, and I will drag this quantity and a modified transition element here, right? So now I will connect my components. I will click C for now, and then I will connect this thing together. And I could see that it has a modifier to it. Um, uh, so if it was if I would have written this library in a much professional manner, what I would have told you is to open the documentation and look for. Okay, I did write something. Okay, so the thing is, once you have a library and you want you have a new component and you want to see how it works, there are two ways to do it. First, uh, you open its documentation, and you can open its documentation by right clicking and clicking view class documentation, and then uh, you can read about how the library is used, and all those and you can read about it. And also, one of the useful things is you can see in which example it has been used. So in this case, it says I have used it in step all the steps. Let me go to step 4, and then I can open this class in model center, and I can see, okay, so in the solutions I have a model where I have used it like this. So this plus perhaps takes the input from the infected category, right? So when you have a new component, the first thing is you go to the documentation, try to read how what it does, and the next thing is try to look for the examples in the use examples section, and try to look into some existing examples that will give you an idea how to better use that particular component. So to repeat the process again, right click on a component, go to class documentation, and get try to read about it, see what are the parameters that it has, and then look at the different examples where this component is used, and try to get an understanding of this component. Right. So I will get back to my model, so which was this one, and then I see that I have a different name called influence transition, and then I will connect my infected to the influence transition uh, component here. Uh, One might notice that in my previous model, I had a nice curved line going from the infected to the transition component. And when you would do it, by default, it's a straight line. So if you want to make it curved, you can select the connection line and then right click and then select curved connection line over here. And then you can play with the styling and such things. Right. So now I have a new um, component here, and if I click on the new component, I see I have two different parameters. So previously I had only the transition factor, but now I have a new a new parameter called as total population. So in my example, I have susceptible as 100 and infected as 1. So the total comes to be 101. Let me just change the susceptible to 99 to keep it at 100. So my susceptible population now is 99, and I have one guy in the infected category. So I will set the initial population to 1. And then if I click on my transition element, I will write the total population to 100. And then let's use a factor of 2 per day in this case. And then we can go back to our simulation results and update it there. Right. So now I have a new component. I added the parameters. Now let's try to simulate again. Let me simulate this and let's see what happens. Right. Okay. So Leo, this behavior looks interesting. So here you see in the new behavior at the start, we have a the rate is slow. And once we have sufficient infected people, the rate increases. And at the end, when the number of susceptible people is less, then it flattens out. Is this what you would have expected?
I mean, yes, because in the beginning, if we have only one person infected, that person will be in contact with less people, right?
Yeah.
So until the other persons in their circle start getting infected, they propagate will propagate it, right?
Yes. And let's try to play around with the transition factor. But what happened, Leo? Now I get a red error saying variable transition dot factor does not exist in model. Okay, so perhaps when we tried to use a different component, what happened was we renamed the component transition to influence transition, and because of that, this controller object is not. Uh, we are getting an error here. So let's try to edit it. In order to edit my controller, I would something happened. Yeah, I would uh, press on this three icons on the side, and then I would click edit, right? So I would press on this edit icon, and it brings me back to my control object editor window here. So now let me just close this and choose my new factor, which is under influence transition. I select my factor, and then slider again, I can select it to 0.001 per day to, let's say, 3 per day, right? And now I could update the broken factor, right? So Leo, do you want to add something to it? Like, once we rename things, sometimes things break, and then I had to update it, right?
Right. So I mean, if they have the same, I guess that if the transitions have the same name and the same parameters, this will not be an issue, right? But in this case, you completely change the
Yes,
transition, so you
yes.
expect.
And this is actually a common problem. Like when you are new to system modeler and you try to play around different components, try to play around this control objects, it is understandable that you would face this kind of problems,
But
right?
what happens if you just rename the component?
Okay, so you mean to say, if I go back to model center and if I right click on my component here, let's say I have a model at some time I figure out that I have a spelling mistake that I want to fix. Will my all my works be lost? Okay, let's try to test that, Leo. So I will right click and go to rename, and then I will change it to transition, right? This was the original name, and let me click OK, right? And now once I have renamed it, let's try to simulate it again. Okay, so now if I go to the edit button, so actually it renamed it properly, and then I didn't have to change anything, right? So if I use a rename option on a component, then I think it checks for similar references in the model plots or in the control objects and tries to update it accordingly, right?
Right.
Whereas if I don't use rename and if I just drag and drop another component, of course things will break.
I see there is an interesting question in the chat.
Hmm.
So in the model,
Hmm.
you manually set the population,
Hmm.
the number of susceptible,
Hmm.
and the infected. So what if you want to make it easier and not having to manually update the like values in three places?
Yes, you are right. The thing is, when I was trying to develop this simple components, I wanted to keep things very simple. The reason being, there are advanced concepts, like I could have a global thing, record and use those things, but I wanted to keep things simple so that if someone goes and they want to understand a model, it would be easier. So I wanted to use the simplest of components without complicating those things, because it easily gets complicated when I create a library with those structures in. And that was the only reason I thought of setting it manually for this case.
Yes, but I guess that you can add a parameter, right, with the
Yes,
population and just
yes,
calculate it from the from
yes.
that value.
Right. So what you're trying to say is, I can have a parameter at the top, and then I can calculate the other values from it. so that I don't need to set the values at different stages, right? So let's say what you're saying is I would do add parameter, and then I would add a parameter to my model. Let's say total population, and then click add. So now it added a value to my model, and then in susceptible. So here I can just write in total population. What was the name? Total population, and I can have the same name, I guess, right? So I can just write total population here, total population. So what I'm trying to do is I have added a parameter at the top level of my model. By top level, I mean if you click anywhere on the modeling diagram, you get this general view, and in that view, then you can add a parameter to it, and that is what I mean by the top level parameter. And here I can add a value 100. And if I want a component to make use of the top level parameter, for instance, if I want the transition component to make use of my top level parameter, I just write the name here. So here for this total population parameter, I will write the name, which is top total population in this case. So now I'm manually linking my component with the top level parameters. And similarly for the susceptible, I can say total population minus 1, right? And then I have infected as 1, or uh, right. And for infected also, one can imagine having a parameter at the top where I can say infected, and then I can calculate it, right? Okay. Right. But I think people might end up in a wrong model for now, so I will just remove it at this stage, but probably we will cover it at a later stage. So you can add a top level parameter and pass it on to your different components. So let's get back to the susceptible, which we had at 99. Transition, total population goes to 100, and infected goes to 1. Okay, right. And then once we simulated this, we got this type of curve, right? And of course we can then play around with it with the transition factor and see how the curve shape changes. And as the transition factor is less, you could see you are having a it slows down the process. Okay, fine. So Leo, so far we have covered, we have seen um, all the components present in our sub library that we have for this session. We have modeled the susceptible and infected, and we have used the transition element, which depends on infected and susceptible population values. So far so good. And we saw the plot from this, and we can say that okay, this is somewhat what we might expect, right? Okay, the next step is in our SIR model we have the susceptible, infected. Now we want to add a new group to it, that is a recovered group. So let's go and add our new group to our model. So let's drag the population group here, and you could see that uh, I'm out of space in my modeling canvas. And what I would want to do is I would want to enlarge my canvas for now. So I can select, if I want to enlarge my modeling canvas, I can select the edge of the canvas, and you can see the green dots being highlighted at the edges, and I can use it to and move it towards the right hand side to increase the space that is available to me, right? So I will click the green icon, I can increase the space. And similarly, if there is a green icon on the left, so Leo, I think you're not muted. Okay, and then if I want to reduce the space at one side, then I can use the green icon, and I can just drag the uh, screen towards the right. And then if I double click, it auto zooms to the white space that I have. Right. Okay. And Let us rename this population group to recovered, and then uh, let's use this. Okay, so now we have a new population group with recovered, and let's keep the initial population to 0. And now I will ask uh, Leo, which transition element now you think we should use between infected and recovered? You already saw three different type of transition elements. What should we use now?
So it's probably the first because the recover doesn't depend on how many are infected, right? So each person recovers at their own pace.
But don't you think that the transition will have some dependency on the number of infected people? Because in the transition element, if I have this transition element and if I have this one, so in this transition element we define number of people transitioning per day, and that is constant, that has no dependencies on the source, on the source population, right? So if I connect it to the infected people, it will have no link to it. But don't you think that if we have more infected people, um, our transition rate should be dependent on that?
I actually don't know. Probably we can test them
Yeah,
both and let's see
yeah,
the
we can
results.
test. Let's start testing with thinking that there is some relation to the number of infected people, because you might think that at the start with more infected people you get more recovered people, and at the end when you have very few infected people, the number of the transition rate will lower down.
Yes, you're right.
Because let's say at the end there are only 5 infected people, and if you have a transition rate of 3 per day, that doesn't work. You need to have some proportionality with this group.
Yes, that's right. So if we have like 100 persons that are sick,
Yeah,
we expect them to recover at certain time.
yeah,
And if you use the first one, let's say, and you set it to one, even if there are 100, that is specifying that only one person of the day is recovering,
yes,
right? So
exactly, yes. And then let's try to give it a another name. I will just have it a name, give it a name, recovery, and click OK. Right. And then I will use the connection line tool and connect the components together. Right. And if I click on transition, we had a factor of 2 per day. Of course, recovery is much slower. So I will go with a slower rate, and let's say 0. Or let's say 1 divided by 10. So perhaps it takes 10 days to recover. So I will have something like that, 0. 0.1 or something, right? And then I have recovered at 0. And now let's get ahead. Let's simulate this model. Right, right. Okay. Uh, so you see that I have a very weird behavior. And the reason being, maybe my transition factor, which I had 0.63, was not good enough. Let me just increase it further. Uh, Not sure why that happened. Right. Okay. So let's go ahead and plot the recovered here, and then let's uh, get the values. Right. So we are getting very big values here for some reason. Let's go back to the model just to try to see if things are all right. We have susceptible 99. We have a transition 2 per day. We have a total population here. We have infected 1. We have a recovery rate. Oh, right. So this is what happened, Leo. Our units changed. So when we had 0. 0.1, our units actually changed here. So I think we should have 0. 0.1 uh, like written like this, 0. 0.1 per day. So when we had this as an expression, when we had 1 per 10, 1 divided by 10, it went back to its base unit, which is always in the SI unit, and it's seconds 1 per second. But here, we should use the numeric values, right? So it's like 0.1 per day, right? Hopefully that should fix our problem.
So
uh, and I think
so
that should
people was recovering like a very very fast,
very,
right?
very fast. Okay. Yes. So this is what we would expect. And this is a common mistake that one might do. Like when you use expressions there, sometimes the unit uh, gets changed to the base units, and that might result in errors. So it's good to note, to keep check of the units.
And how did you notice? Can you show me again? How
Yes,
did
if
you
I go to
notice that
model
the unit
center,
changed?
yes. So the thing is, if I click on recovery and I did 1 divided by 10 here, you could see that here my unit actually changed to per second. 1 divided by s per second, right? So that means 0.1 per second. But what I actually wanted was 0.1 per day. So I think that's what triggered it. So I will just use 0.1 per day here, right? Okay. And let me get back to simulation center. So now this is what we kind of expect. So now the number of people from susceptible is decreasing, uh, and the number of infected people, as you can see here, is increasing. And at a certain stage, when like as the number of people have recovered, the number of infected people goes down. And then one could play around with this, with the different um, transition factors. If the transition factor initially is low, like if the transition factor from susceptible to infected is low, then you could see that um uh, the peak, which was at, okay, it is interesting. Let's do this. Delete from all subplots. Let's say that we have a higher transition rate of 1.3 per day, and let me do take a timestamp. And for that, I will hover near the uh, x-axis, and I press Control and click. So now I have my time snap here. So it was at 6 days, right? And now if I lower the transition rate, then I could see that I have a new the peak now is after 10 days. So there is, so by having a slow transition rate from susceptible to infected, I was able um, to delay uh, the spread, and then the peak was also at a later time, and also you could see that the number of people in the at the peak also reduced. So if I had it um, at 1.3, the number of people infected at the peak was around 71, as you can see here. And then if I have a lower transition rate, and then the peak was delayed, and of course the number of people infected at that stage was 47. So you could see how the initial factor from susceptible to infected has a role to play, right? uh, okay, so Leo, do you want to add anything up to this point, or things have been clear so far?
For me, everything looks clear now.
Won't it be interesting if we can use the Wolfram language and try to test different scenarios? Because as you can see, now once we have a model, we have to use a measurement cursor at different point and try to take the snapshots at different time, try to remember what was the value. It would be nice to see a cumulative value
Yeah, so it
across
would
the
be
year.
nice to compare both cases.
Yes, yes. So let's get back to our notebook and try to see. Okay, um, right. So people who want to try this out, you can take a few minutes, and I will be just explaining what I've done here, and then you can try to reproduce this like this code in the Wolfram language. So here, Leo, what I'm trying to do is I'm using the same model that I developed in that I have saved in my solution step one, and then I am using the parameter values option from the system model simulate command, and I'm giving it two different values. So let's say I want to compare, uh, like if I have a transition rate of zero point 0.8 and if I have a transition rate of 2. And you might also notice that I'm using quantities here. Just is the same reason that if I don't use these quantities in one per day, either I have to convert my transition rates to per second, or I can use quantity to make my life easier, because now I'm trying to deal with per days rather than per second. So now I want to compare what would happen for this two different rates, and you could see here I have plotted, and this is for the zero point 0.8 day, and this is for um, the okay, sorry. So the blue curve here is the first is for 0 0.8. So you can see that I have a lower peak, and the peak is at a later time, whereas the second curve with the orange style here, it uh, it is um, it is way faster. It reaches the peak sooner, and then it has a higher peak, right? Also, so now you could see, Leo, how it how this is becomes much easier, right, to compare two. And here I'm just comparing two conditions. You could also imagine comparing a wide range of parameters that you want to compare. And one interesting thing also I did was, or one could do is, um, I used the uncertainty plot to see what is the most likelihood case. So here I used a uniform distribution. I gave it interval um, here to my transition factor, and then and then you can see how the curve responds to it, right? Yes. So I think I will give a few seconds for people to just to see this code and to try it out. And in the meanwhile, Leo, if you want to add
I have,
something, or
I,
Sergio, if you want to if you have some questions that we should cover, please let us know.
I have a question. So what I'm seeing here with uncertainty plot,
Hmm.
it is, I understand that it's performing like many simulations
Yeah,
with values that go from zero point 0.8 to 2, and then it like aggregates all the results to create this plot and give me like what's the most common result.
yes, and then you could see the this one is the median, and you have the different spread across it. Perhaps Sergio can tell us, like Sergio, like are there other things apart from median and this and the other uh, the bands? Are there other things as well that we can plot using the uncertainty plot function?
Right, you can also plot confidence bands, prediction bands. You can also set different kinds of quantiles or different kinds of confidence levels. Or you can even create your own some function to sample for each time point. But that's more custom.
Right,
Yeah. Mhm.
Sergio. This is something I have not mentioned it. Yes, in our um, yesterday. Like I'm using a something called interpolation points. Can you tell like why is it needed? I don't think it is needed, but in which case should we use interpolation points? Um,
Right. So basically, it helps us. So if you indicate explicitly the number of interpolation points, we explicitly do the sampling for those time intervals, as opposed to the kind of default sampling that we would do. So if your model is really big, or maybe it has a lot of events, or is sampling too many time points, then interpolation points is kind of something that you can use to produce a plot much faster.
right. Yes. Right. Um, Perhaps I can. Uh, so the thing is, this code uh, is for people to try out right now. It was not in the initial presentation that was shared. Perhaps I can share it um, here. I can answer it in the chat itself, so people can copy it and then click send. Uh, answered, uh, right? And then maybe I can make it public, or Robs, if you can um, help me make this public, the answer that I wrote to Stephen here, and so the people can follow.
Yes, one second.
Okay. Uh, okay. Now we have a question from Yap that how would one model transition with a time delay? Right. Okay. So uh, so the thing is, I think Yap comes from the system dynamics field, so that's why he is asking that what if we need to have delays um, in our population group. Uh, so I think what you're asking is, in this population, in infected group, everyone, once they become infected, they're ready to be to pass on through the recovery stage. But what Yap wants to say is, can we add delays for a particular stage as well, right? uh, not with the current model, the simple model that I have for today's session, but of course tomorrow we will be exploring the business simulation library, which has which is more of a industrial or industrial level system dynamics library that we have, and we will explore it tomorrow. And in that library we have stocks with delays, and we have different transition rates. So yes, so not in today's the components that we covered today, but tomorrow when we will cover the business simulation library, yes, there you can have delays on those groups as well. Right. uh, okay. Yes. Leo, we have a question that how could you set total population to automatically be the sum of the two initial population? I think that is using
Yeah,
the
that's
top
the
level
parameter.
parameter, and then trying um, to use a top level parameter and then use in relation with that. Then you can do it. Uh, Probably that, or then or else we will come up with more uh, advanced solutions. But I think the first step is by using a top level parameter and then referring the other parameters in relation to the top level parameter. So you just set the initial thing. um, right. Right. And that would be, if I stay here, so if I click on my model, I go to the top level, I add a parameter which is says total population. I click enter, then initial susceptible, click enter, and then initial infected, enter, and then initial recovered, enter. And then I can say total population to be initial susceptible plus initial infected plus initial recovered, and then I can specify like say 99, 1, and 0, and then I can pass on this initial values to my to my components. Like instead of here 99, I would say initial susceptible, uh, and this would be initial infected, and this should be initial recovered. Right. So now rather than giving uh, uh, um, a value to each of this groups, I am giving it a reference to the top level parameters of my model, and then in the top level I can have this relations over here, right? And so to repeat the process again, to create a top level population, or to create top level parameter, you right click, go to add, and then parameter, and then you can type in the name of the parameter, and then you can do it. Also, in some cases, um, you don't want the users to edit this relation, and you want to disable the editing of this parameter which has a relation to it. And you can right click on a parameter, go to properties, and then editable. We have an option called editable, and we will go make it to false and click OK. So now what happened was I made it this parameter uneditable because it has a relation which I don't want my model users uh, to tweak. So one good idea is define the parameters that you, or keep the parameters that you want people to edit as default. And if there is some relation um, that you don't want the model users to change, you can right click, go to properties, and make this editable goes to false, as you can see here, right? Right. Yes. Okay, Leo, do you want to add anything to it?
No, I think I'm fine.
Yes. Okay. Okay, Sergio. Uh, do you want to add anything to what we covered, Sergio? Like something perhaps on the Wolfram language side? Is there something interesting that one could do that I failed to cover today?
No, not really. As any graphic, you can modify this plot with plot style and all this kind of
Yes.
options. So
One question I kind of remember now, Leo, Sergio, we had like, what is an output? Uh, like when we use uncertainty plot, we have this something called outputs. Like what can we specify here? Is it any variable that we can specify in the model, or are there some specific variables that we should use here?
no, here it could be any variable really that you are interested in. Yeah.
Okay. So for instance, yeah, I will not do it now because I might break things. Okay. Right.
There is a
So.
there is a comment from Stephen.
Mhm.
I guess is how to show the total population value that is calculated when you simulate.
Right.
I think that it's
Uh,
possible to show in the plots, right?
yeah, yeah. When you simulate it, you can, of course, in the plot you can see the total population. Maybe not in the model center. Maybe if that is what you mean, like not in the evaluated form in the model center, because it might be in relation. It might be using relation to something else that is not evaluated in model center. So once you simulate the model, of course, you can plot the total population as well. Right. And as an exercise, if you want to explore this model further, you can think of adding more levels to it and try playing around different values and trying to reason why things happen, or what could uh, what could change. Yes, Stephen, I got it. Like you mean in model center one should be able to see the evaluated value here. Currently we cannot, one cannot do it. Am I right, Leo, or is there a way that I'm missing?
No, I think it's not possible because it does need to compute. It needs to perform calculations in order to determine those values.
Mhm.
Because as you mentioned, I guess that you can write this parameter in terms of other parameter, and it can be in terms of a parameter that comes
It
from
can be
another.
function call or
Yes,
something, blah blah blah.
yes, yes.
Okay, anyways, so let's I think we are 20 minutes beyond our time. Okay, so as an exercise, please feel free to use the block, try to make some changes. And tomorrow we will be exploring the business simulation library, um, which will build upon the models that we have created today, and it will add more uh, more restrictions. It will be much better than my toy model that I am using today, for the sake of understanding this concept. But we will explore it tomorrow. So to summarize, today we saw like how to, when you have a problem, start thinking about which type of libraries you can use. And when you use a library, try to start with the simple components, try to see how that goes, and then uh, start with only the essentials, and then keep on adding as you start understanding each step. and then don't start by accumulating all the components together and then simulating it, because then you will have no idea how each component works, how the relation between two component works. So start by going step by step with testing each component. Right. Okay, then I think we have covered all we have covered all the points that we had for today. Thank you for attending. And if you have any issues, if you're trying with the Wolfram language code or trying it in System Modeler, if you have any queries, please feel free to post it in the community, and we will try to answer as soon as we can. Yeah. Thank you for today. Have a good day. Bye.